So in this first part of the experiment, our job is to torture a dolly. So in question 1, they tell you put the doll on the back end of the cart and then yank the cart forward quickly and describe what happens to the doll. So like that. It's probably most useful in this first question to specifically describe how the doll moves relative to the table rather than to the car. In the second question, we don't want the doll to fall off the cart, but we are going to smash him into a brick wall as hard as we can. So like so. Again, describe what happened to the doll, and it's probably very useful in this question to talk about how the doll moved relative to the car rather than to the table. The third question is exactly like the second, except that this time we're going to give Dolly a little seatbelt. So again, we'll smash him into a brick wall. Again, describe what the doll did and relative to the cart. The fourth question is where you explain the physics of these three cases. So they specifically tell you to think about inertia, the idea of resistance to change. It's also incredibly useful when you're trying to describe these three cases to think about Newton's first law. So Newton's first law is that a body at rest tends to stay at rest unless acted on by a force, and a body in motion tends to stay in motion unless acted on by a force. That one law describes these three cases. You just need to think about how. So in this part of the experiment, you've got a cart, it's got some added masses on it, and we're going to apply forces to the cart and then measure the acceleration of it. You're going to be using the acceleration program for this, so I'll give you a very short refresher on how to use that program later in the video. As always, the first thing you should do is level your track carefully, so put the spirit level on there, make sure that the bubble is centered, and adjust things if you need to. The way in which we're going to apply forces to the cart is we have this mass hanger, and it's on a string, and you attach one end of it to your cart, and then over here we've got a pulley. And the mass hanger just dangles over top of that. And that applies a horizontal force to the cart, so when I release it, the cart then accelerates down the track. Now you are going to capture that motion on screen, get some graphs of it, and as usual you will fit a straight line to your VT graph in order to get the acceleration of the cart. Now we're going to study 4 different cases with the cart on the track, and we're going to compare the second case to the first case, the third case to the first case, and the fourth case to the first case. So the latter 3 are all going to be compared back to the graph we made for this setup. So for that reason, you need to print out 3 copies of your VT graph for every person in the group, because you're going to be pasting that graph into 3 different locations of your lab manual. So this was our first trial. Now I'm going to show you how to do the second trial. For this one, you take the cart and you flip it upside down and you stack the masses on top. And you're going to make a graph of this too. Obviously it's going to be a pretty boring looking graph, but you make one anyway. The point here is that we are still applying this force to the cart, but it's not moving. And why is that? Well, that's because there's other forces involved. So you should be able to explain the physics that result in this cart having 0 acceleration right now. Now there's 2 more trials that you're going to do with the cart, but before you get to that you have to do question 6 in your lab manual. So I'm going to give you that quick refresher on how to use the acceleration program and then give you some hints on doing question 6. So as usual, the programs you need are in the 1100 folder, and we're using the acceleration program. So you have seen this before. So you've got the cart with added masses sitting on the track, and it's connected via a piece of string over a pulley to a mass hanger that's going to accelerate it. So let me demonstrate to you what the data would look like on the graph. So you pull your cart back and you click the start button, and then you're going to release the cart and let it accelerate down the track. Now this here is the bounce back at the end of the track. We don't care about that. Same thing here. It's only this first section here that we care about. So the cart was being accelerated. We expect on the position time graph for that to look curved, and it does. And because it was a constant acceleration, we expect on the velocity time graph to get a perfectly linear line, which we did. Now the manual tells you that you're supposed to print out both of these graphs. I will let you know that it's only the velocity time graph that's worth marks. So you do want to fit a straight line to this linear graph. So you highlight your data and go Fit, Linear Fit to get your linear fit on there. And then, as I mentioned before, you're going to want to print out 3 copies of this graph per person in the group. So click that graph to make sure that it's the active window, and then go File, Print, and adjust the number of copies however you need to. So now let me show you the second case. I will let you know first of all about a little glitch that the program has, and that is you need to get rid of this original linear fit box before you go and try and take more data. Otherwise you won't be able to delete it properly later. So before you take more data, go Fit and then No Curve Fits. That gets rid of the fit box that was on there. If you forget to do that, it's not a big deal. Just shut down the program and reopen it. But anyways, so now I can show you the second trial. So you pull your cart back again, and you flip it over upside down and stack the masses on top of it. And then you make a graph of this. So you click Start and just let it take data. Now obviously that's a pretty boring graph, but it doesn't matter. You're going to fit it. So you highlight a section that looks nice and linear and go Fit, Linear Fit. And then you'd print this graph out as well, but you only need 1 copy per person in your group. So once you've got your graphs, then you can move on to question 6. Now I'm going to talk about question 6, and I've got this zoomed out for a reason though, because I want to talk a little bit about question 5 again. So let me scroll back. You remember that question 5A was where you had the cart right side up, and it accelerated down the track. Now remember I said you had to print out 3 copies of that graph per person in the group. So where do the 3 copies go? The first copy will go here, and you're going to do the second trial with the cart flipped upside down and paste its graph down here and compare the 2. But of that first graph, the 3 copies, 1 copy goes here, and the second copy, if you scroll down to question 7, the second copy gets pasted in here, and the third copy will be in at the beginning of question 8. And in all 3 of those cases, you'll have a second graph on that page, and you'll compare the 2 to each other. So you'll look at the acceleration values on the 2 and see what happened. So question 5, 7, and 8 is where you paste in those 3 copies of the first velocity time graph. So now let me talk about question 6, and I'll zoom in a little so you can read this better. So in question 6, the first part of it is, it says, when a force acts on an object, what happens to the object? So your answer should be some variation on, well, it accelerates. That's not the full answer, but I'll let you come up with the appropriate wording. Now, they don't leave space for you to answer that first question, but it's worth marks, so squeeze it in somewhere, as you do need to actually answer that first question to get full marks on question 6. Once you've done so, then they want you to expand on your answer by talking about 3 other cases you've looked at so far. So you want to say how your answer to this first question helps illuminate what was going on in questions 3 and questions 5A and B. So what was question 3 again? That was specifically the doll on the cart wearing a seatbelt. So we're talking about forces acting on an object. This is the case where the doll had a seatbelt on it. Cases 5A and 5B were the ones on the track that you just did. So cart right side up, accelerating down the track due to the mass hanger, and the second one is the cart upside down, where it didn't move down the track. And again, think about forces acting on an object and what they do. So this all has to do with Newton's second law. So now I'll show you how to do the third trial. The third trial is basically going to be just like the first one with one change. Is we're going to take 50 grams off of the cart and stick it on the mass hanger. And then everything else will be the same. The mass hanger will still dangle over the pulley. Now the reason why we're doing this is that if you think about it, the total mass of the system, everything that's being accelerated, remains the same, but we've applied double the force. So because the mass hanger is now twice as heavy, we've applied double the force to the cart. But the total mass that is being accelerated remains the same. So this will be just like before, where you'll start your program running, release the cart, let it accelerate down the track, and then you'll take your VT graph, fit a straight line through it to get your acceleration value, and you'll paste it into your book. Now one thing I forgot to mention with trial 1 and 2 is it does say in the lab manual for these trials that you should write down the acceleration value. That means you paste the graph in and you need to write down the acceleration by hand. I mention that because it's actually worth a mark, so make sure you do that. In the fourth case, we take the 50 grams off of the mass hanger and we put it back on the cart, but we take the other masses off of the cart. So what we're trying to do in this case is, again, it's very similar to the very first case, with the exception that we've roughly halved the mass that we're accelerating. So we're going to have the same force as case 1, but half the mass being accelerated. And we're going to measure the acceleration of this. So again, you dangle this over the pulley, start your program going, release the cart, let it accelerate freely, capture that graph, fit a straight line to your VT graph to get the acceleration, print it off, paste it into your book, and write down the acceleration by hand. So now I'll give you some hints on how to do questions 9 and 10, which relate specifically to the results of these last 2 trials. So now I'm going to explain very briefly how you answer questions 9 and 10. So question 9 is all about those last 2 cases we studied on the track. So question 9a says if we double the force on the system, but keep the mass the same, what happens to the acceleration? So you go back to question 7 and you write down your acceleration values, actual numbers, and look for an obvious proportionality. So was the acceleration twice as big, half as big, 4 times as big? When you doubled the force and didn't change the mass, what happened to that acceleration? So you should answer this based on actual numbers from your graphs. Same thing for question B, except you're looking at the data from question 8. So if we half the mass of the system but don't change the force, what happens to the acceleration? Again, write down your numbers, identify obvious proportionalities, and then explain what happened to the acceleration when you halved the mass but didn't change the force. Question 10 is then where you bring it all together. They say, how does acceleration depend on force and mass? So you're going to write down a formula that will look suspiciously like something you've seen in class, but you brought it all together based on your data. You write down that law that relates acceleration to force and mass, and then you need to explain how that law helps you explain all the results from questions 1 to 9, so the whole lab so far. So to get full marks for this, you need to talk about all 3 cases with the doll and all 4 cases on the track, and say how this law you came up with helps you explain what you saw in all those cases. So 3 cases with the doll, 4 cases with the track, talk about all of them. So in this part of the experiment, you've got 2 carts, and they've been equipped with these spring bumpers so that we can bounce them off each other. And they also have these wireless sensors, which allow us to detect how much force they're exerting on one another. Now you're going to use a different program to take your measurements here, and getting this wireless sensors to talk to the computer is a slightly involved process. So I've got a separate part of the video where I'll explain how to use the program. The program is called Car and Truck because what we're going to do is we're going to stick a heavy mass on one of these guys, call him the truck, and him the car. And then the experiment consists of running these into each other in different ways. So you'll crash the car into the truck, and you'll crash the truck into the car, and then you'll crash them both into each other. And you'll study the force that they exert on each other and draw some conclusions. So now let me show you the car and truck program. Alright, so here's how we find car and truck. First of all, as usual, open the 1100 folder. When you get in here, however, you'll notice that there are 2 different versions of this car and truck program. So go over here, we want the CMBL file. There's also a Data Studio file, but we want the CMBL file. So we open that guy up, and we now have to arrange things such that the 2 wireless sensors on the carts are talking to the computer. So the way in which you do that is you come up here to Experiment in the menu bar, go down to Connect Interface, select Wireless, and then go to Scan for Wireless Devices. Make sure that the 2 sensors are turned on when you do this. It often takes a couple of runs to find the correct one, so if it comes up and it didn't find anything, just rescan. It happened to find these 2 right away. It may actually find other people's sensors as well, since there's more than one turned on in the room. So look on the sides of your sensors, so on the sides of the cart. Each sensor has its own name. Make sure that you select your 2 sensors out of the list. So I select these and I say OK. Now the next thing I want to do is I want to 0 the sensors. So up here beside the Collect button, there's a 0. So first of all, make sure the 2 spring bumpers on the carts are not touching anything, and just click 0 and then select OK. So once that's done, you should be ready to take data. What you will find when you go to do this is that you'll press collect and it's going to pop up an error message saying, what do you want to do with what's on the screen already? We're just going to tell it to erase that and continue taking data. Then what I'm going to do is I'm going to actually bash the car and the truck together and show you the kind of response you see on the screen while that happens. So I press collect and I say erase and continue because I don't care about what's on the screen now. And now I can start bashing these two things into each other. So I can run the car into the truck or vice versa. I can push them both and it shows me in real time how much force they're exerting on each other. And you look at the amount of force that they exert on each other and draw some conclusions. And obviously this relates to Newton's third law quite a lot. Okay, on the last page of the experiment, there's question 12, and I'm just going to give you a very, very minor hints on how to do this one. So in each of these cases, what it is they've got a little diagram and a force that's being exerted. So, for example, the person kicks the ball. They push on the ball, or the person pushes on the floor because they're standing on it. And in each of these cases, you want to name the reaction force and also draw in the vector. So you would draw a little arrow on this diagram showing me which direction the reaction force points. You also need to name the reaction force. I don't actually require you to come up with an official name. You can just describe in words to me what the reaction force is. So, person pushes on the ball, what does the ball do back to the person? Or the person pushes on the floor, what does the floor do back to the person? You can just describe it in words. I will warn you that the third one is actually quite tricky. So I'm just going to give you a very modest hint in the way I'm wording this. The earth pulls on the person, what does the person do back to the earth? Think carefully about that one. That's the only hint I'll give you.